Welcome to this explainer. Today, we're taking a deep dive into the fascinating geometry behind every single map you've ever used. Whether you're a seasoned geographer or just someone trying to navigate crosstown traffic, the maps you rely on are hiding a pretty incredible mathematical secret. We're going to unpack exactly how cartographers transform our spherical world into flat grids, and why every single map you look at is, technically speaking, lying to you. Here's our roadmap for today. We'll start with the flat map problem. Learn how to visualize map distortions. Look at the geometry of cylinders, cones, and planes, compare the Mercator and Gall-Peters projections, and wrap up with the art of compromise. Let's jump right in. Section 1, the flat map problem. Let's confront a fundamental geometric impossibility that actually affects our everyday lives. Ask yourself, when you pull up a digital map on your phone to find a coffee shop or plan a road trip, are you seeing a perfect 3D representation of reality or a calculated mathematical illusion? Globes are great, right? Their curved surface doesn't distort distances, areas, or angles. But they're definitely not pocket-friendly. We need flat maps. They're cheap, easy to transport, and obviously essential for our digital screens. And this brilliantly illustrates the core issue. Taking a curved 3D reference surface and forcing it onto a 2D flat coordinate grid inherently stretches and tears the geospatial data. Think about peeling an orange and trying to press the rind perfectly flat on a table. It's literally impossible to do without ripping it or squashing it. Cartographers face this exact same physical limitation. They have to transfer points from a curved reference surface onto a flat plane, and in doing so, something just has to give. Moving on to Section 2. Visualizing map distortions. Because flattening a sphere always causes distortions, cartographers needed a diagnostic tool to stress test their grids and see exactly what was happening. Enter Tissot's Indictrix. Developed by Nicolas Tissot in the 19th century, this is a brilliant diagnostic overlay. Imagine projecting perfectly round, identical circles all over the surface of a 3D globe. When we run our map to flatten that globe into a map, we measure how those perfect circles deform. Do they stay perfectly round? Do they stretch into massive ovals? Shrink? It basically gives us a visual heat map of the distortion. Check out how the equirectangular projection handles this. Look really closely at the circles right along the center at the equator. They remain perfectly round and true to scale. The projection maintains true length there. But watch what happens as you move north or south toward the poles. The warning circles completely warp. They stretch out horizontally into these wide ellipses. This visually proves that landmasses near the poles on this map are going to look much wider than they actually are in reality. Now let's see how this works in an equivalent projection, like the mole-wide. An equivalent map, also known as an equal area map, is mathematically designed to preserve the exact size of areas, even if it has to absolutely sacrifice their shapes. Look at the indicatrix here. The shapes distort dramatically, squishing and slanting as you move toward the edges. But mathematically speaking, the actual area inside each and every ellipse remains perfectly constant across the entire map. If you need to compare the physical size of two countries, this is exactly the kind of projection you want. Which brings us to Section 3, cylinders, cones, and planes. How do we systematically manage these distortions? Cartographers rely on some geometric hacks known as auxiliary surfaces. Converting the Earth to a flat plane requires a strict three-step procedure. First, you can't just jump straight from a sphere to a flat rectangle. You have to apply an intermediate shape, a developable auxiliary surface. Second, you transfer the geographic coordinates onto this new shape using strict mathematical rules. And third, you literally unwrap or unfold that auxiliary shape into a flat 2D readout. Cartographers generally translate this 3D Earth using three highly specific geometric shapes: planes, cylinders, and cones. Think of these as geometric molds that you wrap around the Earth. You project the Earth's surface onto the mold, and because planes, cylinders, and cones can all be unrolled or laid flat without tearing, they successfully give us our final 2D maps. So, the crucial point here is that the shape you choose entirely dictates the layout of your final map. Planes give us azimuthal views. Imagine balancing a flat piece of paper on the North Pole. You get a radial view that's perfect for polar perspectives. Cylinders are wrapped around the equator, meaning all those grid lines intersect at right angles, excellent for global grids. And cones? They're basically dropped over the Earth like a party hat. They sit perfectly to map mid-latitude countries that have wide east-west spans, like the United States or Russia. All right, Section 4, Mercator versus Gall-Peters. The choice of which geometric surface to use leads us directly into one of the most heavily debated topics in spatial data processing. It fundamentally boils down to a strict mathematical trade-off. Do you want conformality or do you want equivalence? Conformal maps, like the Mercator projection, keep angles perfect. A 90-degree turn on the map is exactly a 90-degree turn on the actual Earth. That makes them absolutely essential for sea and air navigation. On the flip side, equivalent maps, like the Gall-Peters projection, keep area sizes completely honest. They're vital for accurate geographical comparison, ensuring 1 square inch on the map represents the exact same amount of land anywhere on Earth. Side by side, you can vividly see this mathematical trade-off in action. Look at the Mercator on the left. It flawlessly preserves the shape of the continents, but as you move toward the poles, it wildly stretches those high-latitude areas. I mean, Greenland looks as large as Africa, even though Africa is actually about 14 times larger. Now look at the Gall-Peters on the right. It shows the completely correct landmass proportions. Africa is massive, exactly as it should be. But to maintain that area accuracy mathematically, it vertically stretches the equatorial continents. Africa and South America end up looking like wet laundry hanging on a line. This intense visual contrast sparked a massive debate in the 1970s and 80s. A historian named Arno Peters heavily championed his area-accurate map to counter what he saw as Eurocentric size distortions in the Mercator map, which visually exaggerated the size of northern developed nations. The United Nations even adopted it for a time. However, cartographers pushed back hard, defending Mercator's vital role in navigational math. The impartial truth of the matter? Neither map is objectively wrong. They're simply prioritizing entirely different geometric algorithms for entirely different tasks. Section 5, the art of compromise. Because no single projection can do it all perfectly, we have to figure out how to choose the right map for the right job. When cartographers build a map, they have to select a projection based strictly on the geometry of the region and the ultimate purpose of the data. If you're sailing a ship, you demand a conformal map. If you're mapping global climate change and comparing square mileage, you demand an equivalent map. But often, cartographers deploy what are called compromise projections, like the famous Robinson projection. These are highly complex mathematical models that carefully distribute the errors across the whole map. In a compromise projection, nothing is perfectly accurate, but importantly, nothing is violently distorted either. It just looks right to the human eye, while acknowledging that every single flat map inherently contains mathematical distortion. So I'll leave you with this final thought for this explainer. Every map is a compromise between the reality of our 3D world and the limitations of our 2D screens. The math literally guarantees that perfection is impossible. The next time your car's GPS or your smartphone gives you directions, take a moment to look at the grid. Ask yourself, what specific geometric trade-off is it making to get you to your destination? What angles has it preserved? What shapes has it stretched? Once you understand the math behind the projection, you will absolutely never look at a map the same way again. Thanks for joining me on this deep dive.